Hello everyone, welcome to coinslive. In this video we are going to solve LeetCode problem 793, pre-image size of factorial zeros function. This is marked as a hard problem, but once we understand the mathematical pattern, the solution becomes quite systematic. Let us first understand the problem. We are given a function f of x. This function returns the number of trailing zeros in x factorial. For example, 3 factorial, and 3 factorial is 3 into 2 into 1, like here, and and it is equal to 6. Since 6 has no 0 at the end, so f of 3, that means like this, f of 3 is 0. Our answer of f3 is 0. Now consider 11 factorial. 11 factorial. If we calculate the value of f11, then its value ends with two zeros. F11 is equal to 2 because it is ending with two zeros. That is why our F11 is 2, right? Because that, we can see here, the value of F11 is 39916,800. That is why there are two trailing zeros. That's why our answer of F of 11 is 2. Now we are given an integer k. We need to find how many non-negative integers x satisfy. Fx equal to k. In other words, how many factorials contain exactly k trailing zeros. Let us look at the first example. When k is equal to 0, the answer is 5. This is because 0 factorial, 1 factorial, 2 factorial, 3 factorial and 4 factorial all have 0 trailing zeros, right? Because 0 factorial is 1, 1 factorial is 1, and 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. So no one has a trailing zeros. So there are 5 valid values of x. That's why our answer is 5. In the second example, k is equal to 5. The answer is 0 because there is no value of x whose factorial contains exactly 5 trailing zeros. At first, we might think of checking every value of x, but k can be as large as 1 billion. So as a linear search, it will be too slow. We need to use mathematics and binary search. Now, let us understand what is trailing zeros. Let's think in deep. A trailing zero, how can it be created? Like 10. Let us create 10. So how we can create? 10 is equal to 2 into 5, right? 10 is equal to 2 into 5. So inside a factorial, there are usually many more factors of 2 than factors of 5. Like in 11 factorial, there is 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We can see that 10 can be broken into 2 into 5. So there is 1 5 and there is this 1 5. So there are 2 5 here, and how many 2's are there? 1 2 is here, and 1 2 and 4 can be broken into 2 into 2. That's why 3 2's are there. Now 6 is also can be broken 3 into 2, and 8 can be 2 into 2 into 2 into 2. That's why there are many 2's here. So there are usually many more factors of 2, but 5 is less. Therefore, the number of trailing zeros is determined by the number of factors of 5. Hope you understand. To calculate the number of trailing zeros in x factorial, we use this formula. The formula is x divided by 5 plus x divided by 25 plus x divided by 125 and so on. Like it will increase in the power of 5. We use integer division in every step. So the formula will be floor of x divided by 5 and floor. We will take the floor output. And why do we include powers such as 25, 125 and so on? Because some numbers contain more than one factor of 5. For example, 25 is equal to 5 into 5. So it contributes two factors of 5. Similarly, 125 is equal to 5 into 5 into 5. So it contributes three factors of 5. Let us let us calculate the number of trailing zeros in 11 factorial. We divide 11 by 5. So using integer division, we get 2. Then we divide 11 by 25. Now it will give 0. So the total will be 2 plus 0 will be 2. Therefore, F11 is equal to 2. Now let us create a helper function called trailing zeros. We will use this trailing zero to receive a number x and calculate the number of trailing zeros in x factorial. Inside this loop, we repeatedly divide x by 5. After every division, we add the result to count. When x becomes 0, we stop and return the total count. Now, let's understand an important pattern in function fx. The function is non-decreasing. This means that as x increases, the number of trailing zeros never decreases. For example, f0 is 0, f1 is 0, right? f2 will also be 0, f3 will be 0, f4 will also be 0, right? Then comes f5, sorry, f5. It will become 1 because 5 factorial has one trailing zeros. The value normally remains the same for 5 consecutive integers like f0, 1, 2, 3, 4, and after that f5 is 1. And now, for example, the trailing zero count is 1 for 5, 6, 7, 8, and 9. Similarly, the trailing zero count is 2 for 10, 11, 12, 13, and 14. But there is an important exception. Sometimes the function jumps by more than 1. Let's look at 24. We are calculating F24. So let's divide 24 by 5. What will be the value? 4 by integer division. And 24 by 25, it will give 0. The total will be 4 plus 0, that is 4. So F24 equal to 4. Now for 25, we will see f of 25. 25 by 5 is 5 and 25 by 25 will be 1. So the total will be 5 plus 1, 6. So f of 25 is equal to 6. The function jumps directly from 4 to 6 as we saw. So and it also completely skips 5. There is no value 5. So that is why there is no value of x such that fx is equal to 5. This gives us a very useful conclusion. For every value of k, the answer will always be either 5 or 0. It will be 5 if the value k exists in the trailing 0 function. It will be 0 if the function skips k. However, instead of checking this pattern directly, we can build a more general binary search solution. We are going to create another helper function called firstAtLeast. This function will find the smallest value of x for which fx greater than equal to target. Suppose we find the first value of x where the trailing 0 counts become at least k. This marks the beginning of the range where fx may be equal to k. Then we find the first value of x where the trailing 0 count becomes at least k plus 1. This marks the end of the range where fx is equal to k. Therefore, the number of values satisfying fx equal to k is first at least k plus 1 minus first at least k. Let's understand with an example. Suppose k is equal to 3. The first value where the trailing 0 count is at least 3 is 15. The first value where the trailing 0 count is at least 4 is 20, 15 and 20. So the valid values are 15, 16, 17, 18 and 19. The total number of valid values is 20 minus 15, which is equal to 5. Now suppose k is equal to 5. The first value where the trailing 0 count is at least 5 is 25, but at 25 the count decreases, but at 25 the count directly becomes 6 like we saw earlier. So the first value where the count is at least 6 is also 25. Therefore 25 minus 25 is equal to 0. This correctly tells us that no value has exactly 5 trailing zeros. Now let's write the function first at least. We start left from 0. We will initiate a variable left from 0. For the upper boundary we use 5 into target plus 5, that is right. Why is the range sufficient? Roughly speaking, every group of 5 numbers contributes at least one trailing zeros, right? So the first position related to target will always appear within this range. Adding 5 also handles small values such as target is equal to 0. Now we perform binary search. You can also get the middle value using left plus right by 2, but that will result an integer overflow. But using this formula, you can safely get the value of mid. It will not give the error of integer overflow. Now we calculate the number of trailing zeros for mid. So if the trailing zero count is greater than or equal to the target, then mid could be our answer. But there may be a smaller valid value on the left side. So we move right to mid. Okay. Otherwise, the trailing zero count is smaller than the target. This means we need a larger value of x. So we move left to mid plus 1. When the loop ends, left is the smallest value for which the trailing zero count is at least the target. So we return left. Now our final answer will be that we discussed earlier. Now the final answer will be this. Let's now perform a dry run. We need to calculate first at least 4 minus first at least 3. I am writing the shorthand. First at least 4 minus first at least 3. The smallest value whose factorial contains at least 3 trailing zeros is 15. For 14, uh, 14 divided by 5 is 2. So F14 is 2. And for 15, 15 divided by 5 is 3. So F15 is 3. Therefore, F first at least 3 is 15. So first at least 3 will be is 15. Now let us find first at least 14. So for 19, 19 divided by 5 is 3. Uh, so F19 is 3. For 20, 20 divided by 5 is 4. So F20 is 4. Therefore, first at least 4 is 20. The final answer is 20 minus 15, that is 5. So the valid values will be 15, 16, 17, 18 and 19. Let's try run for k equal to 5. Let's take k equal to 5. We need to calculate first at least 6 minus first at least 5. At 24, the trailing zero count is 4. At 25, the trailing zero count becomes 6 as we saw earlier. Therefore, the first value where the count is at least 5 is 25. The first value where the count is at least 6 is also 25. So the answer is 25 minus 25, which is equal to 0. This means there is no value of x whose factorial contains exactly 5 trailing zeros. As we saw earlier, we discussed this earlier. Let's let's run and submit this code. Okay, let's now discuss the time complexity and space complexity. The binary search runs in logarithmic time. For every middle value, we calculate the number of trailing zeros by repeatedly dividing the number by 5 in trailing zero function. That operation also takes logarithmic time. Therefore, the overall time complexity is approximately big of log squared k. More precisely, it can be written as big of log k into log base 5 of k. The time complexity we discussed, the space complexity big of 1 because we only use a few variable and no additional data structures. Let's quickly recap the solution. First, the number of trailing zeros in x factorial is calculated by counting the factors of 5. Second, the trailing zero function is non-decreasing, which allows us to use binary search. Third, we find the first value where the trailing zero count is at least k. Then we find the first value where the count is at least k plus 1. This difference between these two positions give the numbers of values where the count is exactly k. That difference will always be either 5 or 0, and that completes the solution for this problem. So if you found this explanation useful, practice the dry run once on your own, then submit the solution. Thank you for watching. Follow coinslive for more DSA explanations.